This is a setup we did for the aqua conversion process we developed, and we have produced much better setups now. We have one in demonstration in our new facilities at the University of Calgary. You can come and see the CCIT building expansion, where we have our pilot plant kind of setup for in situ upgrading processes. This is what we have found, for example, with nanoparticles applied to only one stream, the vacuum gas oil. This is not even the heaviest one. This is thermal cracking for that fraction. The steam thermal cracking using fixed bed type of catalyst, which deactivates very fast. But if we use nanoparticles that are then later recovered in a very fine process, then we get to increase the conversion level at much higher than 50% for vacuum gas oil. The same can be done on vacuum residue, deasphalted oil, etc. So many ideas are coming from this type of development. But you may say, why we are still locked with the potential of nanocatalysts? Well, the reasons are simple. So far, upscale demonstrations have not produced transformative results because UD catalysts imply lower metal contents to be employed. And if the catalyst is recycled, then there are further reductions in volumes purchased. And UD catalysts do not require ceramic or other massive supports that typically constitute 80% weight in conventional catalysts. Then the catalyst manufacturers don't have a driving force to replace their business. It'll have to come from academia and obviously those interested in upgrading heavy crude oils. I'm going to skip all these slides. These are just particles produced in different setups to demonstrate that we can understand now much better how the particles are formed and what is the type of particles developed. These are just becoming agglomerated because of the need to bring the sample to a microscope. I'm going to skip all that just to show you also that we have not only developed the chemical and the incorporation aspect, the skid that is needed to bring in situ upgrading with these nanoparticles or to produce a field upgrader of very extremely low cost. We also have a good control on the sedimentation process by developing time-dependent 2- and 3-dimensional convective dispersive mass transfer models. We can have control of the settling of the particles to separate them from the fluid once it has been converted. And also we can also control very well the conditions to avoid in the pipelines during the process conditions to avoid the deposition of the particles. I'm going to skip all that. We did experiments to check the model, and we have concluded that if we get to a 150 nanometers, for example, particle, we won't have any problem of settling in the lines for a reaction on the conditions up to from 200 to 400 degrees C. So it may be applied to in situ if we have, let's say, a SACD-like conditions between 250 or 300 degrees C, if we are using hydrogen, as Dr. Hussein indicated, or for an on-field upgrader based on the use of steam instead of hydrogen. I'm going to skip all over this. This is the time required, for example, for achieving 50% conversion, which is our target, using our nanoparticles. This is the second generation of particles we have made. And we need about a residence time between 1 to 10 days, which is about the residence time that the mobilized oil in a SACD chamber would take to come to the surface once it is around the producer well. So I hope to have convinced you that we are integrating in our center the on-light catalyst preparation method, the how to incorporate the catalyst into the reservoir. These things are proprietary, so we cannot disclose them much. The reactivity, this was supposed to come here, but is a PDF. We have studied the reactivity in the sand media of these particles. Also, the recovery and the activity of the catalyst inside the producer well. And we have developed also a catalytic fluid dynamic model for the in situ conditions. These are economic advantages, but these numbers keep changing, and you may tell me that until you don't do your own calculations, those economics are useless, and they are just for us to guide us on how competitive we might be if we develop an in situ upgrading process via a hydroprocessing, for example, compared to delayed coking and hydroprocessing. And this is without adding the fact that we might be enhancing the oil recovery in the media. But the most important thing, and I think Dr. Hussein also pointed out, is this. We have compared the potential performance of an in situ upgrading process by using also simulators, STARS, Eclipse, and we have a simulation group dedicated to it. And we have found that we could reach, compared to SAC-D and surface upgrading, an in situ upgrading process that reduces to less than 67% the requirement of steam and water, less than 50% that requires of power consumption, and less than 50% of the natural gas demand and greenhouse gas production. And this is just by integrating in the reservoir the upgrading activity to the enhanced oil recovery activity that anyway needs thermal input to be able to mobilize the oil. I think this is all I have today, and this is many more. This is just the people working in my group, but we have also to thank many other professors and in particular our sponsors, Shell, Nexen, Conoco, Total, Repsol, and Alberta Ingenuity, that has now merged into one single organization, ARI, and what was Alberta Ingenuity. Thank you very much.